In our previous videos, we looked at how to make enols and enolates. Today what we're going to look at is something called alpha halogenation. And I wanted to quickly show you how this works under acidic conditions, and then we'll look at the mechanism. So let's do the overall. And I'm just going to put acid catalyzed up here. And it's pretty straightforward. Let's say we've got this starting material here. So cyclohexanone, and we treat it with our catalytic acid. So I'll just write H3O plus and cat underneath. It's important to remember that if we have catalytic acid around, we're going to be in equilibrium with a portion of your enol. And then in the next step, if you have elemental bromine around, you can get the alpha position right here to react. So you should be able to get a bromine to install directly on that alpha position and then go back to your keto form. So let's take a look at this mechanism in a bit more detail. And the mechanism should be pretty familiar. So let's just briefly review how to make our enol using our acid. And I'm going to just show this as H3O plus. And let's actually show this proton. So I'm going to do H3O plus like this. And our first step is going to be protonation of this carbonyl. So we're going to protonate this carbonyl. And then we've got these alpha protons on either side. It doesn't really matter which one we grab because it results in the same product. But now water can act as a base and kick up electrons all the way to that oxygen. All right, so at this point, we've formed our enol and we've regenerated our acid. So this is our enol right here. And like I said, it's important to remember that the enol has a major resonance contributor that we should consider, where the electron density from this oxygen can be pushed all the way down to that alpha carbon. So let's draw both resonance forms. So this would be the second resonance form for our enol, which means in our next step, if we have elemental bromine around, the bromine can act as an electrophile, and then this carbon over here can act as a nucleophile. So I'm just going to write nucleophile. And this nucleophile, all it needs to do is attack this bromine and kick off bromide as a leaving group. All right, so we're almost there. But we still have this proton coming off of our oxygen, and we still have Br minus floating around. So in this case, you can show a proton transfer where some sort of base, in this case bromide, could grab that proton and give you your final ketone product with an alpha bromine plus HBr as your byproduct. So the key feature is that over here, we've got this resonance structure showing that the carbon in the alpha position has a partial negative charge, which means it can act as a nucleophile and react with some electrophiles like bromine. All right, so it's a pretty useful reaction, and I'll show you why it's useful. So let's just write useful trick is, let's say we have cyclohexanone, and we treat it with these reaction conditions. So I'm just going to write H3O plus on top and Br2. This is a one-step reaction, meaning you can do it in one pot. And when we do this, we can get our bromine installed in the alpha position. And then in a second step, we can react it with some sort of base. And this base, what ends up happening is it will go after one of these beta protons. And so I'm just going to show this as base with a negative charge. It can grab one of these beta protons, clamp down, and kick off our leaving group. So this is really just an E2 elimination reaction that we have shown here. And when we do this, we can make a new double bond, and we can extend the conjugation for this reaction. And what I mean by that is now you can see we've got a double, single, double bond. That increases stability. These are really important functional groups in organic chemistry. This is called an alpha beta unsaturated ketone. And we're going to look at these in a lot more detail later on, but really the best way to make them is by first doing alpha halogenation followed by E2 elimination, which is why I wanted to show it briefly. All right, so let's take a look at another example using alpha halogenation. And let's say we've got this ketone, where now we have a methyl group coming off of one of the alpha carbons. So if we think about reacting this with our catalytic acid and our elemental bromine, we could imagine that, well, maybe our bromine will install here, or maybe it will install here. So let's draw both products out, and then we'll try to guess, or not guess, make an educated opinion as to which position the bromine will most likely attach to. So these would be our two different theoretical products. Now the question is, well, which one's going to be major, which one's going to be minor, or will they be made in a 50-50 ratio? Well, let's think about what happens after the first step. So I'm going to do this reaction down here, and I'm going to say when we react this with our catalytic acid, we could theoretically get two different types of enol. We could get an enol that looks like this, and we could get an enol where the double bond is simply on the opposite side. So now the question is, well, which enol is more likely to be created? Well, in this case, this enol over here is going to be more likely because it's more stable, right? We've got a tetrasubstituted alkene. So let's make a note. So more stable because it's tetrasubstituted. Where over on this side, this alkene only has 3 substituents coming off of the alkene, so it's going to be less stable. So this really tells us that over here, that this is the more likely pathway. Meaning it's energetically more favorable. Conversely, if we think about which product that means will be major or minor, that means that the bromine is more likely to form from that intermediate than the other intermediate. So that would be our major product, and this would be our minor product. All right, so hopefully that makes sense. We do have to think about the stability of these intermediates whenever we're doing these reaction pathways. I did want to show you really quickly too, this one's a little bit less common because it's harder to control, but you can do halogenation under basic conditions. And what you could do is, let's say we have this ketone and we treat it with catalytic hydroxide under equilibrium conditions. We only have alpha protons here, so we'll only get one type of enol. And the double bond can only form on that side. It can't form over on this side because if we were to form a double bond over there, we would end up making a Texas carbon, which is not allowed. All right, and then in this next step, you can treat this with Br2, and you could get bromine to install over on that carbon. The main pitfall with this is that this hydroxide is a base which could react with our resulting product, giving us this alpha beta unsaturated ketone that I talked about here, right? Because I said you need a base in the second step. And if you have catalytic base, some of that will be around and it could react to give you that alpha beta unsaturated ketone. So normally when you see this reaction, it's done with acid. However, occasionally you might see it done under basic conditions as well. All right, I did want to show you a slight variation of this reaction, and this is called the alpha bromination of carboxylic acids. And the name of this reaction is called the Hell-Volhard-Zelinsky. I'm not going to be super picky about you memorizing the names of these reactions, but I do think it is important to know what people are talking about if they throw out one of these named reactions. All right, and I'll show you an overview. We're really not going to get into the nitty-gritty of the mechanism, but the first step in the Hell-Volhard-Zelinsky reaction is to react your carboxylic acid with phosphorus tribromide. And if you remember, phosphorus tribromide is used to convert alcohols to alkyl halides, specifically alkyl bromides. In this case, we don't have a true alcohol. We have an OH group coming off of our carboxylic acid, but it still works. So we're going to swap this out and we're going to make an acid bromide. This is highly reactive. And at the same time, what we're going to do is use catalytic acid. And because we have alpha protons coming off right here, we should be able to make a small amount of our enol in equilibrium. So this is just simply that enol formation. We've seen this mechanism a number of times. And just like in our previous example, what we're going to do is we're going to treat this with Br2. And just like we saw with alpha bromination under acidic conditions, this carbon right here is nucleophilic due to resonance. So we should be able to install a bromine right there. When we do that, we'll get the alpha brominated product, but the bromine on the other side is still there. All right, so at this point, we've got our alpha brominated product. We can convert this back to a carboxylic acid by simply reacting it with water. We saw in the previous chapter, these acid halides will react very quickly with water and convert right back to the carboxylic acid. But the benefit to this is that the bromine on the other position is going to stay put. Conversely, you can react this with an alcohol rather than water, and you can end up making a alpha halogenated ester. So really, this is the exact same hydrolysis type mechanism we saw in our carboxylic acid derivatives chapter. All right, there's one last reaction I really wanted to take a look at, and this is called the Haloform reaction. And I did want to make an important note, and this note is that this only works with methyl ketones. And I'll show you why. Okay, so I'm going to use the example we did in lab, where if you remember in our multi-step synthesis, we started out with acetophenone, and acetophenone really only has alpha protons coming off of this side, right? And what I did was I added hydroxide to that mixture, and this hydroxide is able to deprotonate one of those positions. And in fact, this should be under equilibrium conditions. The reality is very little of this is going to form our enolate, but for right now, we're going to go ahead and show this. And when we do this, we're going to end up with a negative charge. And this negative charge can then react with some sort of halogen that's in solution. And this could be chlorine, bromine, or iodine, right? So it has to be elemental. In lab, what we saw was we were able to use bleach to produce a small amount of elemental chlorine, but this would also work if we use bromine or iodine. And what we do next is we just have this react and kick off our leaving group. And then we're going to repeat this 2 more times with the remaining 2 alpha protons. And we should be able to get 3 halogens installed off of that methyl position, right? So like I said, it only works if you have a methyl group coming off of one side, meaning a CH3 group. And the reason for this is that's kind of the requirement in order to make this into a good leaving group, is you have to have all 3 halogens. If you even have a carbon on there, it's not going to be nearly as good of a leaving group. All right, in our next step, hydroxide is going to attack in, kick up electrons to that oxygen. We'll get a negative charge. And like I said, this is set up to be a good leaving group. And we can kick this down and now dump off that carbon. Let me clean up this arrow a little bit. And we're not quite done yet. A lot of times students are tempted just to quit at this point, but we're not there yet because our group that was kicked off still has a negative charge, and it's going to be a pretty good base. And we've got a carboxylic acid, so it's immediately going to steal the proton back from the product that we just made. And we'll end up making a carboxylate salt. And the cool thing with this is that this can actually be used as a diagnostic test. So if iodine is used, this forms a yellow solid. So this used to be actually a diagnostic test to see if your unknown compound was a methyl ketone. You do this reaction with iodine, and if you saw yellow precipitate forming, it meant that you did in fact have a methyl ketone. If you had an ethyl ketone, you wouldn't get any yellow precipitate, and you would know that, hey, this isn't a methyl ketone, it must be something else. All right, in the last step, all we need to do is protonate this using some sort of strong acid. So in lab, for example, we used HCl, and you could grab this proton from your carboxylate, or using your carboxylate, and you should be able to get your final carboxylic acid. So it's a nice way to convert a methyl ketone into a carboxylic acid. All right, so that's where we're going to stop now. When we come back, we're going to look at a lot more chemistry involving the alpha position. Specifically, we're going to look at the aldol reaction.